Okay, the recording started. So the first goal here is to really answer those questions: what, why, and how. Okay, so decision diagrams, again, is a very expanding area with very exciting developments, right? It was initially applied in a very different context for Boolean function manipulations, representation of Boolean functions, and really only recently was brought up to the field of optimization and different related techniques, okay? It's really now becoming the basis of different state-of-the-art methodologies in many fields, just because it really connects with other areas very closely, and it provides some different benefits and features to other areas of optimization, to column generation, to other decomposition techniques that really they can enhance them and we can exploit them in a different way. That's the goal that we wanna focus here today. So it has been applied in sequencing problems, in TSP-related problems, a lot of nonlinear programming, in approximate dynamic programming methods for value function approximations, also in stochastic optimization in a way to encode samples. So it's been really growing, and I think that there's a lot of room for improvements there. So we want to focus on the three fundamental questions here: is what are decision diagrams, if you have never seen it before, why and when should you consider it, and how can you actually apply it? Okay, these are the three main questions that we want to answer here, at least give it a general idea. Again, very casual. Even if we put a lot of material here, if you're not able to finish everything, don't worry, we're going to make this available, and I hope that's going to serve at least for a reference of what the state of the art of what's happening. Okay, so let's start answering those questions. To start answering them, I want to start with a problem. Okay, let's start with problems. We love optimization problems, so why don't we start with one? So a very common problem nowadays, if you've been reading the top journals, you see that more and more problems of these styles are coming up, especially in cloud service. So let's go through the very fundamental of this problem. Suppose that you have a cloud service, let's say Amazon Web Service, that receives a total of I jobs that they need to process. Okay, so every job has a particular profit. If they run, the person's going to pay some particular monetary amount, is going to have some utility for running that service. And every service also requires some type of workloads. So how much CPU hours is going to require from your cloud server. Okay, so the cluster can only process within that time horizon a total workload of capital W. Okay, great. So the objective is how they're going to select jobs to maximize your total revenue. All right. So this seems to be a very fundamental problem. People are studying nowadays it's very pervasive nowadays in different contexts and different variations of this problem with some uncertainties elements. But this is a very fundamental problem in cloud service, right? So let me ask you, what type of problem is this? How would you formulate this problem? Who can tell me, at least in the chats, something? What do you think that how this problem could be solved, or how would you even formulate this problem? What class of problem is this? Perfect. It's a knapsack problem. The knapsack problem we all know, we love, very classical. Everybody understands it, right? So the cloud service problem is essentially a very fundamental knapsack. And you see, many people are studying this problem in different ways. For instance, a very recent paper by Cohen, essentially we have a chance constraint here with some distributions on the weights, but it's essentially a variation of a knapsack problem. Okay, fantastic. So how would you solve this knapsack problem? If you're just given like this with a deterministic version, what would you use to solve this classical knapsack problem? You can use a dynamic programming method, Matthew said. You can use an IP, fantastic. So these are the techniques that we are used to, we understand, because we know that for knapsack, it has some properties, right? So the dynamic programming model, it's going to be the number of states that you have when formula is going to be pseudo polynomial. So maybe if you have a very, very large W, maybe still not feasible for you to address, but mathematical programming would be, for instance, one of the first things that you would also think. You could put that into your Guru, your Cplex, and you're going to solve that in a millisecond, even if you have a billion jobs to allocate, right? But why did we model this way? Why do we think about, for example, mathematical programming or dynamic programming model? Well, there's a variety of reasons why we think of that way. Well, because it's well solved by that way. It's the first problem probably that we learned when we studied mathematical programming in our IP class of 101, right? It has a number of techniques that they use there. It has strong cuts, has very strong heuristics, have a very good branching bound. We know how to branch effectively on this type of problems when we have constraints. And also there are very strong approximation algorithms, right? We even know a lot of the structure about the LP relaxation, the underlying polyhedral structure of this problem. We also have very, very good heuristics. If you just do some sorting here, you're going to have excellent results. So we know a lot of these problems, which is the basis of many of the fundamental techniques that we want to talk about. But let's try to think a little bit more deeply why we are thinking about modeling this way and why we think about problems and how we think about problems when we learn about them. And one theme that is really pervasive in all of that is that we are always searching for some type of structure that we can understand and we can solve it. So this is really intrinsic to optimization and operations research on operations management, right? If you go to AI is a different story where you're trying to make very general data sets. Here in optimization operations, we usually try to find some structure that we can exploit to solve problems faster, right? And when you're developing models, essentially what we are doing is that we are revealing that structure, right? Our model itself is going to give us properties, what type of methodology can we use. If you do a mathematical programming model, you're going to have branching bounds. It's going to give insights, right? If you take the duals of your linear programming relaxation, you're going to learn something more about the problem, either from managerial insights or even to give you some ideas of how to solve. Maybe from the duals, you can prove the optimality using complementary slackness, all those things that you learn in IP 101, right? So model itself is going to give us how to solve the problem and going to give us the structure, right? And there are different types of models that we use, different types of representations. For example, this function here, I don't know, maybe some of you are seeing this function a lot. This is a kind of a logit function, right? When you're looking at functions, what type of structures are you looking when you have functional formulations of problems? Well, when you have this function formulation, we have this called parametric representations, right? You're looking for functional structure. You're looking for convexity, supermodularity, something that you can exploit to solve the problem faster, right? If you have a problem that you have a convex formulation, you're minimizing a convex function over one variable, and the function is smooth, you're going to take the derivative and you're going to find the optimal solution, right? A higher level of this is when you're formulating problems using mathematical programming. So you're going to go there, you're going to be searching for a specific structure, right? You're going to have a polyhedral structure. And polyhedral structure is going to reveal, let's say, facets for you to have strong cuts, to get stronger relaxations. You're going to have to search for unimodularity of your coefficients. Maybe if you have unimodularity, you know that the LP relaxation is going to be the best possible, that your polyhedra is going to be integral. So solving the LP is good enough, right? You can exploit duality to find approximation algorithms, to find new things. You're going to have decompositions. You can use density growth, Bender's decomposition, logic-based Benders. A whole new set of methods is going to open up when you have that particular structure, right? The goal of what we have here today and the goal with the Cire diagrams is to show you another type of structure that we can also exploit, okay? That you can add to your toolbox. Essentially, what we want to do here is that we want to exploit network structure. Okay, which is the idea of the Cire diagrams. So essentially, you're going to have a representation of the problem as a network, and then you're going to have different types of methodologies, different types of relaxations, new things that are going to open up when you formulate the problem that way. For example, you're going to have shortest paths, you're going to reason about paths, you're going to reason about arcs, you're going to reason about discrete relaxations. So it's going to be something a little bit different, okay? But it's going to be something in addition. It's not different or it's not better or worse than other methods, like if you have a MIP. They are actually complementary. You can use both of them. And actually, the most effective techniques, right, they confirm the most effective techniques are the techniques when you start involving all of them, when you find the ways to communicate this different structure, communicate, exploit them in different ways. Okay? Good so far? Any questions? Okay, so let's open up. Let's see how we can exploit these different properties and how we can leverage that. So before we can understand it, let's see what it is. So what is the Cire diagrams in an optimization view? Again, there is a very large field in different areas, a lot of papers in Boolean function manipulations. We use that a lot in our results, okay? But the focus in optimization is a little bit different. Even some words that we use, you're going to use in a different way, okay? So what is the Cire diagram? The Cire diagram is going to be a layered, cyclic network that is going to give you a set of solutions explicit. We're going to have an explicit representation of the problem as opposed to an implicit representation. So implicit representation is when you write the math, right? You are not looking at the solutions. Solutions are implied by that polyhedral or that system, the system of equalities or inequalities, right? Here, we could actually look at the solutions when we represent them explicitly, okay? So suppose that you have this optimization problem. You have the single knapsack, binary variables, and we want to optimize this function. A decision diagram is going to be essentially a representation of the set of solutions to this problem, okay? So each one of the layers is going to be associated with one variable, okay? So we have x1, x2, x3, so you're going to have 3 layers here, okay? Some notations say that we have 4 layers because every node has to be in a layer, so we can think that you have actually 1 layer, but the first 3 layers are going to be associated with each one of the variables, okay? The arcs going to represent the variable value assignments. So for example, here we're going to have 2 arcs because they correspond to 0, 1, the possible values that you can assign to a variable. So either you're not going to add the item or you're going to add the item. X1 is going to be 0 or X1 is going to be 1, right? You're going to have dashed and solid arcs, okay? And in this case, the arc weights will also be the contributions to the object function here. So for example, if you set x1 to 0, you're going to have a 0 contribution. But if you have set x1 to 1, then you're going to have a contribution of 8. Okay, so this is the most fundamental representation of the scenario. When you represent in that particular way, the paths of this diagram from a root node to a terminal node then represents a complete solution, complete assignment to the variables, right? So if you take this path here, 0, 1, 1, you're going to have x1 equals 0, x2 equals 1, and x3 equals 1. And then the contribution to the objective in this case is going to be 0 plus 5 plus 2. So you're going to have an objection function value of 7. So this is the nutshell, what is a decision diagram. So if you're trying to optimize this function here over the decision diagram, what is the path that is going to give you the best possible solution in this problem? What do you think? How now can you optimize this function? It's going to be exactly like Angel said, it's going to be the right one. It's going to be the longest path. So essentially what we are doing is that we are reducing the problem to a longest path problem in this particular graphical structure, right? So this longest path gives an optimal solution. And that's it. If you want to know what is the decision diagram, of course, now there is a whole new things that we have to exploit here. But if you want to know what the decision diagram, this is it. It reduces the problem to a network type of problem, right, where we have the longest path. And the other path is also going to evaluate some solutions, but we're going to have the complete representation of the problem. Any questions?
Can I add to that for a second, Andre?
Go for it. Go for it.
So Andre calls this an explicit representation of the solution set. I also can maybe argue that it's an implicit representation. Why? You're not actually writing out all the solutions, and there can be an exponential number of solutions that you are representing in a polynomial, maybe, size graph, and how you actually can deal with kind of the balance between the size and the representation that you have is something that we'll talk about, of course, later on in this tutorial. But it is more explicit than an IP, that's for sure. But you can also somewhat view it as an implicit, because you're not, like, I can't tell you all the solutions immediately from looking at this, but they are there, right? So I think it's an interesting way of kind of thinking about it.
Absolutely. So let's say it's in between a very implicit representative constraint set and an explicit where we would have actually a table with all the solutions, because we still need to find the path to evaluate. Thank you, Dave. Yeah, absolutely. So again, let's make a conversation. Every comment that you want to make, please, everybody feel free to join me, okay?
David had a question in the chat for you. I think this is a good time to try to answer that, because it's probably going to lead to the next part, Andre. How did you encode the constraint?
I think that's what we're going to show now, how we're going to build the decision diagrams. And there are many ways to build them, and there are many ways to construct them that are going to impact also how they can be useful to different methodologies. So Dave, give me a quick second, and then we're going to get there, okay? If you're still in doubt, we'll show you later. Any more questions? Good. Okay, so let's continue. So what type of problems are we considering? So before we actually start describing how we're going to formulate the problems, I just want to restrict our space here a little bit to the class of problems that we're just going to handle this. Again, this is not only the set of problems that we can formulate with decision diagrams, but just to make our life a little bit easier here, right? So in this tutorial, in this introductory slides, we're just going to focus on discrete optimization problems. Not required, but let's just focus on that, okay? So all some decisions are going to always belong to some finite sets. So let's say bounded integers, but can be also fractional values as long as they are finite, okay? This is the very general structure of problems that we're going to consider here. I have to maximize some function g over some set of constraints that I'm not specifying if they're linear or not, but still I have a finite number of constraints and a finite number of variables. All the variables itself, they have finite domains, okay? Now, so X is going to be a vector of discrete decision variables. There are constraints that define the feasible region, okay? And Gx is the objective function. This is already, you can make your life research this type of problems, of course, because it's very general. I know many classes of deterministic, stochastic programming models, even some classes of stochastic dynamic programming models are encoded in this way. So the different problems you can formulate like this, okay? But I'm just let's just focus our scope so that we don't incorporate continuous variables. Now we're just going to leave this hard part for Daniel to address that. Good? Okay, so again, please don't miss Daniel Davarnia's work. Very interesting about the representability of these diagrams, but we're going to get there. Okay, so to answer David Bernal question and many of our questions I may have now is, okay, what can we do with this? Okay, how can we get toward the solution approach? And so I really want to flesh out the different components of different ways how decision diagrams can be incorporated in different components by making parallels, let's say, with mixed nature programming, which is something that we are all used to. So what are the different recipes or elements that compose a MIP, for example? Well, you're going to have a type of modeling language, right? Something that imposes structure to your problem. In this case, for MIPs, we're going to have linear inequalities, but for decision diagrams, we're going to have recursive structure. So we're going to impose some structure there to model, to represent it. We're going to have a lot of properties that we're going to infer from that structure, inference structural properties, right? Here we're going to have network properties, arcs, layers. We're going to talk more about it. Relaxation and bounding, right? MIPs are too hard to solve. We don't know how to solve them. They'd be hard. So what we do, you relax them and branch. So what is the relaxation part associated with decision diagrams? Because they can get too large, right? So we cannot formulate them. So it's going to be something analogous to LP relaxation, but for decision diagrams. Other one is search and solution methods. Well, if you relax, you don't have an optimal solution to your problem. You need to somehow do some kind of enumeration. And we're going to also have our own version of branch and bound. You can do traditional branch and bound with decision diagrams, but you can do something a little bit more that we're going to get there. So we're going to have search and solution methods, just like we have with Bender's column generation. We're going to have our own version there. Okay. In primal methods, how can you generate heuristic feasible solutions from that? Even DP, you have the greedy approach. MIPS, you have feasibility pump. We're also going to have a way to do that with decision diagrams. So let's start with the modeling language. The first one, which is going to be the basis of almost everything that we do. Okay, modeling language. So there are many ways for you to compile, for you to construct decision diagrams. There are many, many different ways. Solution table lookup. So let's think about the most straightforward naive ways, not the practical ones. Okay, the most naive ways. You can always build all the solutions of your problem, like enumerate, create a table with each one of the solutions, and then you can basically create a graph based on that. There is a ways of how you can do that. It's going to be more compact. Actually, it can be exponentially more compact than the table itself. But it's not something very practical, but you can do it, and it has some uses to do that in some situations, particularly for column generation. You can actually build the branching tree of your MIP. You can actually construct all the branching tree of your mixed integer programming model associated with your problem. And then as long as you have a fixed variable order for each one of the layers, you can start then merging the nodes, as we're going to see in a little bit, and procedure called reduction. You can do that. But then if you build a MIP, why would you even need to build a decision diagram? But it's possible, okay? But there are many ways that you can do it. But there are very intrinsic connections between decision diagrams and dynamic programming. And we're going to leverage those connections to provide a systematic way how you can build these decision diagrams. And then it's going to help later on how you can also relax. And what is the connection between relaxations and other existing techniques from optimization? So what is dynamic programming? Dynamic programming are models that exploit recursive structure as opposed to polyhedral structure, right? So now, there's every discrete optimization problem, especially if you have finite domains, you can always write as a dynamic programming model. Not that it's a good idea. We don't do that often because I think we're just not used to doing it, but there are a lot of discrete optimization problems you can write as a DP, and very classical papers for Karp and Held. This is an amazing paper if you want to read, if you want to learn more about these connections that I strongly suggest here in finite state process programming, showing what is the connection between discrete between dynamic programming and reformulations of problems like we are used to. What are constraints in a DP, right? How do they map each other? So a good read, but we're going to cover the basics here. Okay, dynamic programming. I'm going to give very quickly, again, you don't need to go, we're not going to go through dynamic programming. We don't need to have all the techniques there, but I just want to give you an idea how you formulate problems and just to get a flavor of it. Everybody's used to the knapsack. I'm sure you're forming the knapsack, but you can do much more. Okay, so what is the intuition about DP? So when you're solving a map, right, when we are all solving maps, what we are doing is that we are enumerating variable value assignments, right? So think about the branch and bound, right? The branch and bound, you're taking a variable and you're fixing to 1 or 0 and so on. So you enumerate very valuable assignments in a smart way, like you're removing nodes, use the relaxation and so on. In DP, the idea is a little bit different. The idea is that it's more effective to enumerate states than enumerating value variable assignments. That's the idea, the intuition behind dynamic programming. So there is a functional form, a representation that you use for dynamic programming, which is a recursive form. It's called the Bergman equation, if you've ever seen it. So Bergman equation, essentially, you're trying to find, let's say, the optimal solution, which is called the value function for a particular state. So you are in a particular state of the system that you look. Then for that state, you want to find an action, you want to find an assignment of one of your next variable so that you get the maximum reward that you can collect plus a continuation reward. So this is essentially what you're going to get if you take that first decision. So for example, for the knapsack, right, what we are doing is that we are making one decision at a time. We're deciding to pick an item or not pick an item. And when we pick an item, we're going to get the reward for picking that item, the profit of scheduling that job in the cloud server. And then I want to take the best possible, I want to see what is the continuation reward, what's the consequence of picking that item to the remaining solutions, okay? So this problem is decomposed into I stages because every stage you're deciding an item that you're going to pick or not, okay? It's still a little bit vague. We're going to make an example for the knapsack. But every time that you are in a state and you pick an item, you're going to get a reward for that item, right? And essentially, you're going to move your system to a state. You're going to transition your system to a state. When you pick an item, you lose a little bit of the load that you have because you're going to consume that capital W, right? How much you have the load of the system. So then the state itself is going to have a summary of all the past decisions that you made up to arriving at that stage, right? And then we want to pick the action that maximizes that reward. Right, this could still be a little bit vague, but I think it's very clear when you see an example. Everything becomes very clear, but at least we have things more or less formalized. We have to optimize object function by picking one item at a time, or one item at each one stage. And every time that you pick an item, for example, you're going to get a reward plus some continuation value. What's the consequence of picking that item? So let's see an example, so that is much easier. But just to complement, this is a whole area by itself, of course. There are number of techniques to solve it, forward, backward recursion, value iteration, policy iteration, even in stochastic setting, there's a huge number of ways to solve it. But that's out of the scope here. Okay, so let's see an example of formulated dynamic programming, just so that things become super clear. So how are we going to formulate that cloud serving problem or a knapsack, right? So at every stage I'm going to decide whether I'm going to pick an item or not. Okay, I'm going to decide whether I'm going to pick an item or not. The state of my system is going to be the load of my knapsack. How many items, or what is the remaining left loads that I have, or how much, it doesn't matter. How much weight I already consumed from the knapsack. Okay, this is one of the formulations. So let's say if I pick one item that have a load of 10, so I'm going to transition my system to a state of 10 where I already picked a load of 10. And action is going to be whether you're going to pick an item or not at each one of these stages. Okay. So for example, if you have this formulation, this is going to be the formulation of your knapsack problem, right? At every stage, you're going to decide on one variable. So you order your variables, you order your items. So at the stage I, you're going to decide whether you're going to pick the item or not. To pick an item, they state the current load of the system. The current load of the system is going to. Okay, so I'm sorry. This happens online. If you don't mind, let's see if I can block the. Of course, of course.
Isn't that amazing? Yeah, let me know if it sounds okay now.
Okay, okay, I removed the. Okay, so let's suppose that we have a, but I have a fire alarm still here. But let's say that we have an item. So every stage, we're gonna pick an item or not. We're gonna add the item to the state. Okay, we're gonna load up the state. And I can only pick an item if my capacity of the knapsack has not been exceeded. Okay, if I pick an item, I'm gonna have a profit, and then I see what's gonna be the best possible value that I get with that when I transition to that new state. Does that make sense? Is that clear for everybody? Good. Thumbs
Yeah,
up or thumbs up.
If I can add something here, it is a little bit different than the classical DP model for knapsacks, right, Andre?
Yeah, it's a little bit different. I could also, but it would be equivalent if I remove the state by the load that is left. Both of them would be equivalent in this case.
Right.
Right? Okay. So perfect. So this is the profit. It's going to be what's going to be the optimum solution with that new knapsack load that you have. Good for everybody? Okay, great. So the optimal function here is going to be the value function of this 0 when you start with no loads, right? And then you see what's going to be, you keep updating this value function here, you essentially going to enumerate, and you're going to do, you can solve this in different ways, but this is the traditional formulation of knapsack. And we're going to see more examples, so don't worry if it's still a little bit vague, okay? So what is a decision diagram for the dynamic programming model is there are also many ways how, if you give me that Bergman equation, how I can actually build the decision diagrams, multiple ways, all right? So the most used way is going through, is called the top-down compilation and variants. There are variants of that, so something that I'm going to show here. And the other way is called incremental refinement, where we're going to build decision diagrams by separating one state at a time. Okay, but here we're just going to go through top-down compilation. If you need more reference to show other ways, let us know. We're going to send you the reference. Okay. In all of them, what the decision diagram is a compressed representation of the state transition graph. Okay, it's a compressed representation of the state transition graph. It's not a state transition graph. It's a little bit different, but it's a compressed representation of that. Okay. If you want to think intuitively, the states that you can reach, all the possible loads that you can reach, they're going to be the nodes of the diagram. And the actions, whether you're going to pick an item or not, they're going to be the arcs of the diagram. Okay. So let's see how this works. Let's look at the top-down compilation. So we're going to start at the root nodes, and then we're going to expand the nodes one at a time, the layers one at a time. All right. So suppose I have this problem here, and I have the DP. Okay. So I'm going to have my decision diagram here. I'm going to have two types of arcs, right? Either I'm going to include that item, or I'm not going to include that arc, and I'm going to have each one of the variables. Okay. And the state of my state, as remember, is the current load of the knapsack. Okay, so I'm going to start with the root nodes because I know that the decision diagram has to have a root node. Okay, so I start at the root node, and the root node has my root state, the initial state of the system. In this case, is 0. I have no load for my knapsack. Okay, so now what I'm going to do is that we're going to start extending the layers one at a time. So here I can have two extensions. Either I'm going to add the item, or I'm not going to add the item. If I don't add the item, I'm going to transition to a state of 0. It means that my load is still going to be 0, right? I'm not changing the loads. Now, if I add the arc, right, and I add the arc, my load is going to be updated by 2, right? It's the load of adding that item there, and I have 2. So then I expanded and I updated the states accordingly here. Good. And then I can also do the same thing for this other node here. Well, I can, for this item, I can not pick the item 2 or pick the item 2. If I don't pick the item 2, I'm still going to have 0 here. And if I pick the item 2, then I have the coefficient of 1 here. So then I'm going to move to state 1. Okay. Now here from 2, what happens is that the load of my knapsack is 2, right? So if I add the item 2 here, I'm going to go to a load of 3. And this load of 3 is going to violate the constraint because I have my constraint. I cannot exceed the load of the knapsack. So in this case, I can only have a 0 arc. I cannot have a 1 mark. So the capacity here remains as 2. Is that good? Is that clear for everybody? Perfect. Now, when we go to the next stage, what's going to happen is you're going to start having some merges, right? So it's the same story here. Here you have 0. Here, if you add the item, you're going to have a coefficient of 1 in this variable here. So you're going to go to a state 1. For this node here in the middle, when you don't add an item, you're still going to have a state of 1. So you're going to move to the same state. You don't need to have two states that are represented using the same value here. So you can just direct that arc to that same node. Okay. And the same here with 1. If you add the item 1, then you're going to go to a state of 2. Here, you cannot add anything, and you get to a 2. This is the state transition graph of the dynamic programming model. Essentially, you're mapping the states, and you're mapping the arcs as the actions, if you pick an item or not, and you have the state representation. So this is something that is known for ages. But this is kind of similar to the decision diagram. Do you agree? Kind of similar, but there are some things that are different. What was one of the things that is different here? Any idea what one thing that you did see in the decision diagrams that you didn't see here? Yeah, we don't have a terminal node, right? We don't have a terminal. We could actually go there and then merge into the terminal nodes. Another thing about the decision diagram is we didn't talk about states in the decision diagram, right? Which is also interesting. We don't talk too much about states. We really need to have states, right? So this is still, by the way, I forgot about the rewards. I can't forget them. The rewards here, just the reward of applying that action in that state. Right here is just the contribution of the knapsack. So in the first stage, you're going to have 8. So if you put the item, it's going to have 8 here. Here, 0 is always going to be 0. Here, if you have the solid arc, for 2, you're going to have 5, right? So the coefficients, I think it's easy. But this is not necessarily still a, so Anthony, thank you so much. I forgot about the values of the arcs. I hope that you're happy now. So here we have the state transition graph, but it's not exactly a decision diagram yet, but we're gonna get it. Okay, good, thumbs up. Okay, so what differentiates this from a decision diagram? So a decision diagram, there's a very special operation called reduction. This is something in addition to a decision diagram that is something where we can exploit the network, the combinatorial structure that is implied by this graph to get even a smaller representation of the set of physical solutions. Okay, right. So what we can do is that we can take somehow the structure of the graph to reduce it even further. And this is called reduction. So let's see this step of the reduction. The idea of the reduction is that we're going to look at nodes and see nodes that are equivalent in some way. What are nodes that are equivalent? Nodes that are equivalent are the ones that they have the same type of arcs leaving them, right? So, for example, this node here has a 1, 0 arc, and this node has 1, 0 and then 1 arc. So they cannot be equivalent. So the nodes are equivalent when they have the same arcs leaving them, and the arcs are going to the same nodes. That's when the nodes are equivalent. Now, can you see any equivalent nodes here from this graph? So 2 nodes that they have both the same type of arcs leaving and that they're going to the same nodes. Can you see any equivalent nodes? I can already see 3. The terminal nodes, exactly, Matthew. The terminal nodes, they're equivalent, right? They don't have any arcs. So they could be merged, right? So what I can do, this idea of finding these equivalent nodes and merging them is one of the main things of the decision diagrams. That's why they're so compact. And they have been basically used for, they have been critical of Boolean function manipulations. So let's see a little bit further about this reduction operations, okay? First thing about the reduction is that the states can be gone, which is now, that's how we are now differentiating a little bit from DP. We don't need the states anymore to do reduction, okay? So the reduction operation, essentially, we're going to start from the terminal and then we're going to go up. Okay, we're going to start from the terminal and we're going to go up. So here, Matthew already was excellent, and then he or she identified that we can actually merge these nodes here into a single node. So exactly, we can just merge them into a terminal node. Conceptually, this is already a decision diagram. Now we have a root node and a terminal node. And now we can get to reduce decision diagrams where we essentially apply this reduction throughout the graph. We apply this reduction throughout the graph. By doing this reduction now, I may have had new equivalent classes within the graph. Somehow they are showing some symmetry in the set of visible solutions, right? So now what are the other nodes that are becoming equivalent? These 2. right? They have two arcs, and they're targeting the same nodes. So I can actually go there and I can actually merge them, right? Because it doesn't matter how you arrive in these two different nodes. The set of completions, the set of solutions from this node to the terminal, they're going to be exactly the same. So you don't need to have this redundant representation. You can just merge them into a single node. Good? Right. So then we have this merge here. And now we cannot have any different types of merging. And we are good to go. This is a reduced order decision diagram. Order because you have a particular variable ordering, and it's a decision diagram because you have this root and terminal and they satisfy the essential properties. All right. Okay. So this is a reduced decision diagram. Of course, there's a lot of different things we have to talk about, what happens to the costs and so on. But this is one thing that is really critical within the decision diagram theory. All right. So first is that the reduction, doing this reduction, oops, I see the transcript that has been enabled. All right, I hope everybody can see. Okay, so the reduction is going to be a polynomial size operation the size of the graph, in the sense that if you do this bottom up, you can reduce the graph, it's going to be polynomial in the size of the graph. So it's going to be a very small, it can be a very, it's going to be an effective procedure that you can do on the diagram. Okay. Second, for a particular variable ordering, if you have a particular set of, if the variables are ordering this particular way, then this is proved to be the smallest possible decision diagram that you can have, both in terms of the number of nodes and the number of arcs. Okay, it's going to be the smallest decision diagram that you can have for that variable order. So, and that's one of the main things, because if you actually, there are lots of examples where this reduced graph is exponentially smaller than even the state transition of the DP, which by itself already has a lot of compression because of these states. So it's going to be it can be in many cases a much, much smaller graph. Okay. Now, if you work with the DP, you want to think about the connection. Okay, what happens to the states? What is the connection? Actually, this is by itself a new DP reformulation of the problem that we obtain. It's just that it's on a particular state representation that we don't know. It's a state that that's the most compact state that you can have to represent that particular system given that variable ordering. Just that we don't know the state. The states you're finding additional equivalence between the states. All right, but if you're more interested in that, let me know. Okay, let's give another example, because here it's introductory. Let's give more practice. Okay, knapsacks, everybody knows. Everybody knows you can solve as a DP, right? It's not new. But then we can have a lot of different optimization models that we formulate as DP. We're going to have completely different views of how to solve the problem. We can leverage all this theory that we are deriving using this feedback. Okay, so it also reveals novel network structure that we can exploit. So we want to give here a different example of a different problem. And I want to talk about the maximal independent set problem. We're going to give other examples here. And what is the maximal independent set problem? I believe that everybody here already have seen it before, right? So what is the maximal independent set problem? I give you a graph, and I want to find the maximal weighted set of vertices such that no two vertices within this graph are connected by an arc, right? So I give a graph G interacted with vertex weights, all right? And then I'm going to find a subset of pairwise no adjacent vertex with the largest weight. Here is going to be vertex 2 and 5 with a weight of 11, okay? Because there is no edge here, now I cannot pick any other edge. If I pick 1, 3, or 4, it's connected to, so I can pick it up, all right? Good. So let's think about the dynamic programming formulation for this problem, right? So who would ever think about a DP formulation to solve independent set problems? Only Dave Bergman would think about this crazy recursive formulations for problems. So we did spend a lot of time, right, Dave, a lot of different models thinking about it. And it was, I remember, he came up one morning with a board. I know how to do this. In the basement of a Tepper, Carnegie Mellon, he came up with this idea. So let me tell you that, which actually was the basis for a lot of the methodologies that came up later on. But what is the state here? I don't even need to write the DP formulation. The state here is the set of eligible vertices. What are the vertices that can still pick from that graph that is still available to add to your independent set? Okay. So here my R is going to be of two types. It's also a binary variable. So either I'm going to include that vertex or I'm not going to include that vertex in my independent set, right? So as always, we're going to start with a root node. Okay, what is the state here? The set of eligible vertices. I'm going to assume that I'm going to begin with an empty independent set. So I don't have any vertex in my independent set, so all the vertices are eligible. I can pick any of them and add to my IS, okay, for my independent set. Okay, so now we're going to do the same game as we did for the knapsack, right? We're going to have one layer for each one of the variables, which in this case is going to be for whether you're going to pick a vertex or not. And then I'm going to decide whether I don't pick that vertex. So if you don't pick that vertex, what happens is that that vertex becomes ineligible, right? You just remove it, so you cannot pick that vertex again, right? Or you're going to pick that vertex. So let's say you're going to pick vertex 1. If you pick vertex 1, what happens is that vertices 2 and 3, they become ineligible, right? Because they are adjacent to 1. So the only vertices that are eligible here is going to be vertices 4 and 5. Good? Make sense? Okay. Now, we're going to keep playing the same game and have the edges here. The edges, the cost of the edge is going to be either 0 if you don't pick it, or 3, which is going to be the weight of the vertex independent set, okay? Then you can do the same game again. Here, if you pick vertex 2, then all these vertices are going to become illegible except for 5. The same thing, 0. And then you just keep building that way, right? Eventually, you're going to find two vertices that are equivalent. In the case here, they have the same states. If they have the same state, it means that the continuations are going to be the same. And you can simply merge them. You don't need to have two additional representations because they are the same state. They're going to lead to the same completions here. There's this Markovian property. Right, and then you finally have your final decision diagram, right? And the longest path here is going to be, sorry, it's 11, not 9, but here I wrote correctly, just wrote, but it's going to be 0, 4, 0, 0, 7. Good with everybody? This is another example. Interesting thing here is that you can prove that this decision diagram is already reduced, that no more reduced operation is going to, you cannot reduce it for, okay, so this state representation for independent set is really strong. It's the best possible representation that you can get for this graph. Independent sets in general, in terms of the combinatorial structure, they are very special in many, many different ways. They don't have any variable ordering that is certain to be polynomial for any type of graph. There's other classes of graphs where you don't have a polynomial variable ordering. They have a lot of structure in independent sets, so one of those structures is this one. Good? Everybody's fine? All right. There are many other examples. So just a lot of papers that we have now is, for example, you can, oops, I just have a question here. From Ianzu. Algorithmically, when building a BDD, do you want to merge as you go, like in the example, or merge bottom up after a BDD is built, or both? That's an excellent question, Ian. I would say that this is an open research that many people are looking into different ways of how to do that, right? Ideally, you want to merge as soon as you're finding two nodes that are equivalent. You want to identify conditions when they're equivalent. That's one of the works that I believe Thiago Serra is going to talk later. One of the works he did. When can you merge nodes? Many cases, identifying when two nodes are equivalent, even for the knapsack case, is empty hard. So you want to sometimes wait until you build them up. Okay. In practice, many times in practice as well, if you can build, sometimes you just build a non-reduced and then you reduce it later on. If you can build a full complete graph, sometimes it's just faster to do that way, implemented wise. Do you have any comments, Dave, on that?
No, I think that's right? The sooner you can identify it, the better, but it could be NP hard to decide on whether you can merge two nodes. So there's a balance, just like, in branch and bound, you can spend time branching or you can spend time finding cuts and doing inference, right? I kind of think of it as the same seesaw battle, right? I mean, you could, in principle, you can always, if you were willing to solve a MIP, most of the time, you would be able to tell in some sense if these two are equivalent, right? You can enumerate every single possible completion underneath them, make sure they're the same thing. If they are, put them together. If they're not, separate them. But of course, that might take too much time, just like doing a pure cutting plane approach is not practical for solving a MIP. So I think for most practical problems, when you are representing and solving it by a single DD, I find that the best balance is to do something really quick and polynomial, even if it's not exact, and then at the end go back up. But it depends, right? Because if it's too big, then that's no good. But of course, then we can relax, which we're going to talk about later.
Perfect. I also have another question from Nathaniel Ramos. Some problems have inherent symmetries in their combinatorial structures being pegged, for instance, where there are many orderings of the same beings, but the cost is the same. Excellent question, for sure. In the case of the DIS, are there any reductions to merge those symmetrical nodes? Great question. I would say, I think my answer here is that the connection between classes of symmetry that you identify with DDs that are imposed by the variable ordering and the problem class is still a little bit unknown to the best of my understanding. So the problem with different beings is that, from my understanding, from what I know, is that you're going to end up reordering different variables, the different constraints in different ways, right? And so you may lose some of the symmetry if you're trying to put everything in the same decision diagram. And something that Dave is going to tell you something later is a way to exploit this actually if you have different decision diagrams for each one of the beings where you can exploit that symmetry in a better way. From my knowledge, you do identify some of those reductions from the beam packing when you do this mechanism. I automatically identifies those symmetries, but the connections, even there are some connections with the orbitals and symmetric branching, if you knew about that, if you ever heard of, it's still a bit unknown and to explore.
Yeah, I would. The symmetry that you do get from DDs is symmetry with respect to feasible completions. And that is sort of really cool, right? Because like when you're solving a MIP, you don't necessarily know that these two nodes actually have exactly the same endings, right? And that is a symmetry there, right? It's symmetrical with respect to the feasible completions underneath you, or when one is subsumed in the other. But maybe we'll talk a little bit about that later on. But it's not the classical symmetry breaking stuff is, I think, different than the symmetry that you get from DDs. But I like Andre, I don't know if I have the answer.
Yeah, we don't know. If you want to explore it, it's open. It's definitely open. Yeah, we don't know. And yeah, more about symmetry. In the third topic today, Thiago is going to talk more about symmetry too. It's a very exciting topic because it relates to a lot of problems that we have in maps and so on. So Thiago, he's gonna handle that question for us. Thanks, Thiago. All right. Oh, we are almost out of time. So before, I think that David is going to talk about relaxations, but let me just very quickly talk about, there are a number of different problems that you can formulate like this. Okay, and there are a lot of sequencing problems, TSP-related problems, where you do have natural dynamic programming models that you can extend to decision diagrams. You have very interesting formulations. We're going to talk later today. And most important, even nonlinear discrete functions. This is the paper of David and we show that you can actually formulate nonlinear functions, which if the domains of the variables are discrete, as finding paths in this graph here, in a decision diagram kind of graph. And again, the cost becomes a little bit more complicated when you do gain a lot of power because you're essentially you're revealing network structure from nonlinear functions. And so you can exploit cutting planes approaches, you can exploit different ways of relaxing and finding bounds for those functions, and you have special case for some modularity, is that this is very broad. Anything that you can formulate, for example, with a DP, you can exploit this framework of reductions to unify symmetry and make it a little bit smaller. But really, what we want to do now is, okay, how can we do it, right? How can we leverage this network to try to solve problems better, assuming that I can build that. So let me just give you 1 minute of something that is going to be really important later on. Is I just want to draw a connection between these DPs and linear programming. If we draw the connection with dynamic programming, let's draw with linear programming. Okay. So what we are doing is that we are reducing the optimization problem to a longest path on the decision diagram, right? We want to find the longest path in the graph. So, for example, if we draw the graph using top-down compilation of your favorite technique, then you want to find this longest path. Okay, but you can also formulate this problem as a linear programming model, right? Where you can actually, send 1 unit of flow for the root nodes and then satisfy balance of flow constraints. And you want to find the longest path problems or finding you're solving this as a network flow problem when you're saying one unit of flow throughout the problem, right? And this polyhedral perspective, this representation of the diagram as a network flow model or as a longest path model or through the longest path polytope is one of the bases for many of the decision diagram approaches that we have now, okay? So what is the network flow model? It's the same one that we studied in optimization 101, okay? So you wanna send one unit of flow through the root nodes, okay? And then you'll satisfy the balance of flow constraints through the nodes of your diagram, and then you want to maximize the flow cost, in this case, or the flow rewards, right? And if sometimes you can have shortest path problems, then you have the same type of flow. Remember that the graph is acyclic, so this problem is polynomial in the size of the graph, right? The size can be exponential, but it's still polynomial there in the size of the graph. So the root node has a flow one, you have inflow and outflow of the graph, okay? Now, one thing that is very important is this network flow is an extended convex formulations of the feasible solution, something that Bell proved in his dissertation, is that this is a ideal extended formulations of the set of feasible solutions, in the sense that this polyhedral is integral, right, the network flow model, and then the path is going to give you an integral solution associated with the path that is the longest path. So it's a perfect formulation, and a formulation at different dimension, higher dimension, where the extreme points are the feasible solutions to your problem, and the one that optimize the value, the linear function here, the reward, is the one that gives you the optimal solution. Okay. All right. So there's a nice connection to DPs. I don't want to go now. That is the duo of the linear programming approach to DPs. Okay. We don't going to go there, but if you're curious, I know. But what I want to say is that let me just connect everything before we continue. Okay. What is the connection with everything? So if you have a decision diagram, you have a network flow model, right? Representing all the set of feasible solutions to your problem, right? But if you have a DP, you also have a linear programming model. So this network flow model is actually the dual of the linear programming model associated with a DP. But from DP, you can also get a decision diagram. What I want to say here is that these models are all connected. And many of the things that the state-of-the-art techniques that are built on these decision diagrams, essentially they are identifying these different connections and leverage the structure that these different connections they exploit. Which is essentially what we're going to do majority of the time is going to build diagrams in some way, get their network flows to generate cuts, or we can get the DP to get the states and see how they connect to the, or compress the states of DP in a state aggregation way, or we can get the problem, formulate the linear programming model, and get better formulations based on the convex hull of some subset of the constraints. Many of the things that we do are going to leverage these different connections. All right? Okay, so before I go and pass it today, and we have a quick break to pass today, let's just say that everything we are doing now is still maths. We're going crazy here, right? This doesn't make sense because the diagrams are still exponentially large, right? Who's going to build a full decision diagram to a complete optimization problem, right? And that's what we need to address here. There's this inherent curse of dimensionality. And there's an intuition because why that happens, if you understand, is because in DP, the constraints are mapped to state variables in the sense that for every constraint, you need to have an associated state that controls if the constraint is being violated or not. And if you only add one additional knapsack constraint here, in our example, you need to have another state controlling what is the left-hand side, what is the load of these other constraints. So the more constraints knapsacks that you add here, then you're going to start multiplying the states, the number of nodes that you can have, by all the possible values of the weights of those knapsacks. So that's when you start having this huge growth. Of course, if you merge these graphs, it can still be super small, but there's no guarantees for that. Okay, and then that's why writing the exact decision diagram is usually impractical. So this, because I don't know how to address this, I'm going to leave it to Dave to address at 11:15. So let's just give a quick break for everybody to breathe. We're going to be here answering any questions that you may have, but then we're going to go to relaxation inbound with our amazing Dave Bar. Okay, I'm going to stop sharing right now, or maybe I'll just leave it here. Yeah,
you can leave it there, and thank you, Andre. I think that was very good and a very good introduction, of course. So yeah, why don't we take a break till about 11:15, and then I will jump into dealing with the size issues.
I'm just going to stop recording for a little while, okay, until we have this rest session, and we continue.